Okay, welcome everyone to this December edition of the TCIPG series on resilient energy delivery systems. We're really pleased to have Dave Whitehead with us here today. Dave's a very old friend and associate of TCIP and TCIPG. In fact, I believe that he was a speaker at our first industry workshop in 2005. 9 or 10 years ago, depending on how you count it, and has been a big supporter together with his company of TCIP and now TCIPG ever since. You can see the question that's his title, How Would You Know? And I'll let him explain what he means by that, but let me just tell you a few things about Dave. Maybe among other things, I'll start out by saying that he is a graduate of Washington State University and hence one of, if you will, our TCIPG school alums. And we're happy for him having that distinction as well. He's a professional engineer. He's the Vice President of Research and Development at Schweitzer Engineering Laboratories. And he oversees SEL's Security and Information Services Department, as well as the Government Service Division. He's been at SEL since 1994. He's been hardware engineer, research engineer, and chief engineer of the Government Services Division. As I said before, he has a Bachelor's of Science in Electrical Engineering from Washington State University in 1989. And an MSEE from RPI, Rensselaer Polytechnic. He's a senior member of the IEEE, and he also chairs the Power and Energy Society substation C6 group that addresses cryptographic protocols in substations. He's a holder of 43 patents with several other pending. But to say what I said at the beginning, both he and Schweitzer have been incredible supporters, interactors with us on our research in TCIPG, and in fact both motivated and been the recipient of research results that we've made. So Dave, I don't want to take any more of your time. Thank you very much. And
thank you very much, Phil. Everybody can hear me? We're good? Okay, so the topic for today is how would you know? And it's kind of a loose topic, if you will, and it kind of makes people grin when you say it. And one of the reasons, or the reason we came up with this topic of how would you know, came about from a meeting where what would happen if, say, a circuit breaker opened up in a substation? You know, is that... It could be a number of things, right? A program could be wrong in a relay. Maybe the circuit breaker is just faulty itself. Or maybe there was some kind of cyber intrusion or something like that. So the question really comes back with, how would you know if something was really going wrong? And what are the tools we have available to us to take a look at the situation that are already there without adding any more devices or elements to our present systems, to take a look at analyzing the data and the measurements we have to figure out, was this a normal operation, was it a mechanical failure, or there's some other thing going on inside a substation. We wrote this, the original paper, and there's a link at the end of the presentation to it a few years ago, and we focused on the cyber aspect of it, but towards the end of this one, the latest thing that's been of concern to people, especially with the implementation of synchrophasers, is now time. So it's a combination in this presentation of both time and cybersecurity. But before we get started, right, one of the things we like to talk to our young engineers when they get out of school and they come to us, right, they've been working for their senior research projects and they're really focused on some kind of cool technology they developed, right, whether it was part of their senior project or maybe a great class they had, and it could be cybersecurity, it could be encryption, it could be anything. One thing we like to remind these kids is, what is it that we're really doing? What is our purpose? It's not about a particular technology or encryption method. Rather, we're in the energy business. Our job is to provide energy to allow safe, reliable energy to our customers, and we're part of that, working with utilities and other people. So, from our perspective, what we look at is who are the customers and what do they expect from energy? And really, when you come home at night, you expect safe, reliable, and economical delivery of electricity. When I come home home, I walk through the front door, I want to turn on the lights, and I expect them to be on. So that's my expectation as a consumer. On the other side of the equation is the supplier, and he wants a reasonable return on his investment. And you could ask me, Dave, what does that have to do with anything with cybersecurity? And it has a lot to do with cybersecurity, right? These are why we put cybersecurity elements in place, or add another transmission line, or put in another generation stage. All of these things have to be thought of as a whole, from the capital asset purchases to the implementations of new technologies for serving these two key components of the electric industry. We go back to Thomas Edison and Sam Insel. Anybody know who Sam Insel was? We got some people. Sam Insel, his official title was personal secretary for Edison, but he was essentially his right-hand man. And he, up in Chicago, was the one that really guided the electric business going up there. So he is a key figure really in the electric industry as we know it today. And some folks have said that, you know, if Edison had come back, he wouldn't recognize the power system today. And I'll take exception to that. I think Thomas Edison would really understand. Now, he may not understand DNP protocols and things like that, but I bet if you explain it to him, he'd get it really, really quickly, right? So the basic fundamentals of this generation, transmission, and distribution wouldn't be lost on them. These guys really set the foundation for us thinking about electric power systems. And Insel had this great statement, unless we fulfill our primary duty to the public, give absolute continuous service, we fail in the obligation that we have undertaken to the community, accepting a franchise from the city to manufacture and distribute energy in the community. And really is what he's saying, all aspects of what we're doing here, from building the generation, the transmission, and the cybersecurity aspect, how we control, how we optimize the power system, comes down to that absolute continuous service. And that's what we really need to keep in mind as we go about coming up with new solutions. How does it fit into this big picture? So our challenge is, you know, it's not just cybersecurity, which I saved for the last one. The electric industry is a tough one. They have a lot of external challenges. It's not just a matter of creating some new technology, but getting plants, or being able to build plants, lines, and subs is being very difficult, right? One is the permitting processes and all the other things that go along with it. People certainly don't want 500 kV lines running through their backyard, but they want the benefit from the 500 kV yard. So getting plants and transmission lines built is hard. Regulations, subsidies, mandates, CO2, all these other things are another external contributors to some of the challenges we have. Intermittent sources and consistent loads. That is, you know, certainly from the power protection and the delivery standpoint, is becoming a big challenge for us. We used to have dams and thermal units with big spinning masses, and now what we have is essentially a bunch of power electronics from wind turbines and you know, solar voltaics, and they don't behave, it's certainly from a protection standpoint, the way these big masses used to work. So we have these kind of technical challenges with the generation changing. And conversely, our loads are changing from, say, really resistive ones to constant power ones, you know, the switching power supplies, data centers, things like that. We have the stability, thermal limits in the age of equipment because we're not building lines. We're trying to push our lines to as hard as we can, get the most efficiency out of them. And that gets back to why cyber is so important, right? It's this efficiency concept that we're trying to maximize with the present state of our power systems. Customers are less patient with outages, though I got to say most utilities do a fabulous job. If you look at the number of nines of the availability of electric power, utilities are doing a fabulous job of keeping the lights on. A challenge we have is aging workforce, and I'd also add the dynamics of what we need the workforce to do. So it used to be we had people that are really power system experts, and they needed to know about machines and transmission lines and circuit breakers. But with the advent of, say, synchrophasers and time distribution and protocols and stuff like that, the role of an engineer at a utility is dramatically changing. Not only does he have to be a power system expert, but he has to understand Ethernet protocols and things like that. So it's a big, big challenge for him, and a lot of opportunity, certainly for what you guys are doing here at TCIPG, to educate, innovate, and then be able to deploy these new technologies throughout the industry as our industry continues to change. And then finally, I'll say our challenge is cybersecurity. And not only is it very, very important to ensure that if we're going to use cyber means for controlling and optimizing our power system, that it is also very, very secure because of the dramatic impact and the reliance we have on electric power. One thing I'd like to make is, and this is key, I don't know if this is blasphemy or not, but power systems operated for 80 years without cyber controls. Right? We designed the systems to be standalone. They measure the elements that are operating circuit breakers or governors on generators or exciters. They didn't need cyber controls necessarily for them to be able to optimize, or excuse me, to run the power system. What the cyber is really it's a convenience, but not a requirement. What we need the cyber for is this wide area view to optimize the power system, but not necessarily to run it on a, to run it. So this is a little bit for Pete, because we got to throw some power stuff in here. Can't all be cyber control. But protecting the power grid, if we break down our power grid, we have essentially 3 different areas. We have the generation, those could be thermal plants, nuclear plants, hydro plants, photovoltaics, wind turbines, etc. We step that voltage up so it's easy to transmit through our transmission system. We step it back down to a more reasonable voltage to distribute through to factories or our homes, and then we step it down to a little bit more to get it inside our house. And this is, we'll take out the pretty pictures. This is essentially what the system looks like. It's generation, transmission, and distribution. This is a fun thing I like to remind. I've heard every once in a while that, the power engineers, they're Neanderthals. They don't get this high-tech stuff, like layers of security and stuff like that. That's not true. Power guys understood, overlapping zones of protection from day one. So they've always built in security, so that in this picture we have a generator where it's on the left-hand side, where the box also includes the green square box there, which is a circuit breaker. And conversely, the transformer relay protects both of those circuit breakers. So the power industry is well versed in these overlapping zones. So they get the concepts of having layers of security and redundancy and backup protection for all kinds of different things. So they're well in tune, I think, with the ideas of cybersecurity and what we do. Real quick back to do I really need wide area communications to operate the power system? Well, one of the easiest elements is an overcurrent element. If the current's too big, we go ahead and trip the circuit breaker. No communications required there. If we get a little bit fancier, we can coordinate our protection using voltage and currents measurements. So here we have a 21 element, which is a distance element, and you can see where the load is out on the right, and ideally what I have is a big V and a little I, the impedance is going to be purely resistive, so my load is going to be out to the right. If I have a fault, what happens is my V gets really small, my I gets really big, and I come inside this circle, and that circle is set to protect a particular zone in a power system. So if I come inside that zone, it's time to trip the circuit breaker. I can have these relays at both ends of the line. They can coordinate each other. Again, no communication required. So we really can't operate the power system without communication. We just lose some of the benefits for optimization. When we were able to add communications to the power system, we did get a great benefit, certainly from the protection side, of line current differential. And line current differential really is based on Kirchhoff's current law, that the current going into one node has to equal the current going out of the node. And if they don't, and certainly in a power system on a transmission line, that must mean it's going into the ground or someplace we don't want it. So we trip the circuit breaker. So it's a very, very easy concept. It's it can protect the entire length of the line. The challenge is you need to be able to share that current differential information from one end of the line to the other. That's when we started introducing communications into certainly the protection side of things. And it's a great benefit. It gives me total protection on the entire line. However, I have now introduced the communication channel, and the communication channel can fail. So one of the opportunities, or one of the things that we do as protection system engineers, is we say if my communication channel fails, I'm going to go back to that 21 element, that backup one, where I don't need the communication. So there's a lot of play that goes back and forth between relying on the communication system and what happens if I don't have it. Can I still operate the power system in a safe manner? And the answer is yes. This is the SCADA system in 1960, where we have a guy in a substation, and if he needs to open something, he walks up to the panel and pushes a button or twists a switch. And that was the communication, that was the SCADA visualization board. There wasn't, 6 or 7 monitors up there running all kinds of historians and GUIs and HMIs and things like that. If you really wanted to get fancy, you could get a call from say an operations center that says, hey, go ahead and close that circuit breaker in over there. So that was the wide area control, if you will. So even back in the 60s, we had, a way to operate the power system without the cyber mechanisms we have today. But the question really we have is, can we make this cyber convenient secure? And when I say convenience, it is convenient because it allows us in a wide area and in a local way to optimize the power system. So cyber information represents a physical system, and what I'm talking about is our electrical systems here. And that is the huge advantage we have over, say, the financial guys, right? My bank account is really just a number in a database. There's no physical meaning, well, it's personal to me, but there's no physical information necessarily in my bank account information. However, the information that our systems are monitoring, measuring, represent current flows, voltages, circuit breaker status, and things like that. So the data we're getting matches some physical entity or thing out there. The other advantage we have with our systems is they really are over-measured. If we go into a substation, 3 relays may be measuring the same voltage sensor that's on, say, a 230 kV system. So we have multiple devices doing the same measurement. We can use that information as checks against each other. If all 3 relays are saying it's 230 kV, well, that's a pretty good indication that everything's okay. If one of them doesn't, you know, pulling that information back to, say, a SCADA system, there's probably something wrong there. Either the sensor has failed or someone may be, you know, manipulating data. And often, there are multiple ways to monitor, control, and allow access to the systems. So that's an advantage to us, and then we can have divergent routes of data that we're trying to measure and monitor. So this is a quick example of a typical HMI you might see in a substation. It kind of illustrates the point of this over measurement. Up at the top is a 230 kV bus. There's 2 circuit breakers that bring the power down to transformers that step it down to 69 kV. And if we see at the top, we have currents being measured for both that are flowing through the circuit breaker. We're also over measuring the voltages. So the voltages on the 230 kV bus are being measured by the relay on the left and the relay on the right. Similarly, we have the same thing we get down on the 69 kV. If we wanted to do some data checking on the bottom left-hand corner, coming out of the step-down transformer to the 14 kV system, we have current flowing out of that, well, it's breaker 1218, a relay measuring the current flowing out of it, and then to 2 feeders below it, and we can do some quick summations of those. So there's ways we can use these measurements, these over-measured systems, to make checks or qualify what's going on in the power system. And that's really powerful when we sit and think about it. I didn't have to add really any more equipment to the power system. Rather, I'm using this data that is already there. And we could start talking about big data and things like that, but there's, you know, this is really, we have a lot of information available to us that we can use to validate what's going on in the power system. So there was an industry meeting a few years ago, and there was an incident, or a supposed incident, at some facility, and one of the participants stood up and asked a question, you know, how would we know if our systems were being cyber attacked? And it was, you know, it's kind of a simple question, but it got everybody really sit back and thinking at the time is, how would you know? What do we have at our disposal to figure out what was going on? And so we took that idea and we started writing a paper on it. It was kind of a notional paper, and the premise was there was an engineer, and he walked into his office, and there was a report on his desk. This happens to power engineers all the time. There was a circuit breaker operation. And so his job is to figure out, well, was it a normal circuit operation, or was it an abnormal one? And the premise goes along of all the steps that a power engineer needs to do to figure out, you know, or quantify or analyze what was the operation, normal or abnormal. And he goes through a handful of steps. You know, was there a power system? Was there a fault on the power system? You know, was somebody in the relay making setting changes when the thing occurred? So there's a whole list of things. And finally we get down to, well, none of those things were valid during the time of the circuit breaker operation. So what else could it be? And that's how we go down and start talking about perhaps the cyber aspect of this. And I'll kind of walk through some of the challenges that we have with all the cyber inputs and outputs we have in our systems. But here's a typical control system notional diagram. At the top, we have our SCADA and EMS system. So we have SCADA operator stations, a historian, the HMI server, and then a control network. On the outside, we said, well, there's a DMZ and some firewalls, and it may or may not, depending on the utility and how what their procedures are. There may be some connection to the billing department, the dispatch department, and maybe the planning and operations side, depending on how. But ideally, they're segmented and segregated from the SCADA network we have up there. Below the SCADA, we have what I'll refer to as network appliances, and those could be switches, routers, front-end processors for modem banks. They'll go out to various substations then to collect data or issue operation commands or pull in volts and bars. And they can do that through various mechanisms. They can be, if it's a legacy system, like we're showing on the left is a substation 1, which we'll refer to as a serial substation. So it'll have modems set up into it. And on the right is a more modern substation. Will be an Ethernet-based substation. So we have lots of varying types of communication coming in and out of the substation, certainly based on the age of the substation. And remember, the challenge we also have with our substations is substation 1, it may be a serial substation, but it's doing its job. It's doing a great job. It protects the power system. It trips on faults when it should. It can receive SCADA commands. So just because it's a serial substation doesn't mean it's bad. It doesn't mean we should go and do a forklift upgrade of it. And the other thing is we probably don't have the capital to do that anyway. So just because it's old, well, relatively old, right? I shouldn't say it. I'm old. Those substations probably aren't as old as me. Doesn't mean we should go and replace it. And then finally, we get to the IEDs inside the substation. So in substation 1, we have some modems. We have a communication processor that is connected to relays, an HMI. It'll gather up all that data and then be able to present that up to the SCADA HMI. And over in the right-hand substation, the Ethernet one, will have switches, HMI servers, workstations. Depending on the substation, maybe the switch or the router is talking directly to the more modern IEDs. And then finally, there's some more communication links we use on the protection side that aren't necessarily directly connected to the SCADA side. We might have a SONET multiplexer that is connecting all the substations together, and they'll be sending line current differential information over those links. We may even have a radio link connecting up two substations, and then it'll be sending pilot wire communication back and forth. So what you can see is we have a diverse set of communications from legacy serial stuff to modern either SONET or IP, all of that stuff used so that an operator back in the control center can have some operational situational awareness and use that to help drive the power system to its most optimal state. Okay, so where are the point of exploits? And I'll go through this pretty quick because I bet you guys are all cyber experts here and have seen many of these before. But first one is if there's an external network access, right? We could come in through the engineering access on the left. I might be able to come in through the, say, the billing department's network access into the SCADA system. There's links between the SCADA master at the control center down to the various substations. So that's one set of possible infiltrations. There's also our man-in-the-middle attack, so that could be the SCADA link from, say, the control or the substation back up to the control center on either the substation 1 or 2. I could also try to gain access on that SONET multiplexer. That may be a little bit harder. Or on the radio links, I can overpower a receiver and send data in through the radio receivers. There's always a malware opportunity where if somebody goes in and wants to, say, upload a new driver onto a system for relay settings, there's an opportunity there for an exploit. And that could come at the operator station through the LAN, or even at the substation where the operator is trying to upgrade perhaps his firmware. USB sticks, we've all heard of stucknets and the challenges that represents to our industrial control systems. Engineering communication access. This is, depending on how the utility uses it, I may be able to dial in directly to the substation. I may have to dial somewhere into the operations center, and that will route it through a VPN back into the substation. But certainly engineering access is a point of infiltration. for these devices. SCADA communication access, that would be my DNP servers, my through either serial links or TCP/IP, network connections. Real-time control back down to the bottom where I could try to infiltrate on the SONET multiplexers or the radio links. Indirect or direct access, again, those are the people ones. And this is probably the hardest one to detect, because what happens is there is a trusted source that has access to our networks or our devices that could cause us problems, either put in the wrong firmware or put an intentional bug into the system. Denial of services, this is for the engineering access. That's an annoyance. It'd be nice if I could get my data to see what the problem was, but if I didn't, I could eventually just drive out there. From a protection standpoint, if there's a denial of service, that's probably a little bit more bigger deal. The thing we got to remember is protection guys are paranoid folks, right? So if their communication link went down, generally speaking, they have fallback mechanisms in place. So if there's a loss of communications, their secondary protection will protect the power system. Malicious injection of data, again, usually coming from operators. It could come in through the serial links. Software upgrade exploits. There was something going around the other day about somebody's website that got hacked, and they were actually downloading malicious code, if you will, right? Or it wasn't authorized code from the particular vendor. So this is, when we wrote this paper, there wasn't a lot on this. We thought about it, but now we're actually seeing some stuff in the news where a site got hacked, and what you thought you were downloading really wasn't the code from the original company. So that's an interesting one to keep in mind. Data playback. Again, we record what's going on, and through, say, the SONET networks, the radio links, or the SCADA ones, I could spoof the operations center by injecting what is supposed to be, normal operation, and there was really different things happening out in the substation. Again, the fun one about this one is to be able to do a successful data playback over a wide area on a power system, you have to touch a lot of different things, because the system is so over-measured, and there's so many different ways to get data into the system that that is really a tough thing to do. Database manipulations, obviously we can get into the database and manipulate, whether it's you say a Pi server or something like that, is an opportunity for exploit. So there's a whole handful of different ways that data can be manipulated or otherwise spoofing various different parts, whether it's in the control center or say down in the substations. And so we sat back at this point and said, what are the inherent capabilities of devices we have in the substation or communication equipment, or even up in the operations center, that we can use today to help identify if I've been probed, attacked, or otherwise compromised. And we just started looking around at the devices. And so there's things called alarm contacts on the devices, and it kind of sounds like an old technology. Essentially what it is it's an electromechanical relay, and when the relay or the IED turns on, it opens up the contact, and if I were to lose power to the device, or the device has the power supply stops working, the contact closes. Typically what is done is you map that contact output, that physical contact, to say an RTU or some other signaling device, and it can transmit the status of that IED back to an operations center. And historically what they're used for, or what a lot of people have used them for, is just for that signaling. The device is healthy or the device is not. One of the things that we did way back with the first relay is we also used the alarm contact to pulse. And so if you were to go into the access level where you could change settings, the contact out would pulse. And it's essentially an independent channel from the regular relay to signal somebody that they got into the relay, which an operator in a SCADA system could say, hey, there's somebody in the substation, there shouldn't be anybody in the substation, why did the contact alarm pulse? So these are little subtle things you can use today that are built into the devices. There's sequential event reports, and we've used those from the power system side, day in and day out. They monitor contact input statuses, output statuses, anytime something changes within the we call it the relay word bit, but any of the status for protection elements all get logged in there. They also log stuff like power up, power down, or settings changes. So it's really like the power engineer's version of a syslog. And those things are inherent in many, many IEDs at the substation level. We have metering and monitoring capability. The IEDs today measure fundamental RMS voltages, voltages on the power supply, contact input statuses, and all that. All of that stuff is a recording of what's going on in the power system, and we can use those bits of information to see if one element, say voltages, is being manipulated somehow, and compare it to one that is not being manipulated. Communication reports, all IEDs, or at least the ones we're using for line current differential or signaling or that, have communication reports, and they'll tell us the availability of the channel. The availability of a protection channel should be at 5 nines. If we're seeing that there's intermittent problems with the channel, like our availability is going down for whatever reason, whether it's the equipment is starting to fail, which would require us to go out and fix it, or I'm being spoofed, or some other means where the channel is being interrupted, we can use these communication reports to flag alarms and use that as indication that there's a problem going on. And then finally, the devices these days are very, very flexible. So we can make essentially security alarms, if you will, customized ones by using programmable logic and contact I/O. So I can say, if the door is open and nobody gave us permission from, say, the operations center, I could lock down ports or something like that. So there's a lot of flexibility that we can use to tailor a custom profile inside these IEDs with this programmable logic. At the network appliance level, we have, well, certainly network traffic monitoring. We can expect a certain load on our networks. If we exceed those particular thresholds, we can alarm on those. There's communication alarms for, say, ports are down, ports are up. Computer operating systems have system logs and auditable reports. Whitelisting, maybe I should have put that one on the top. Everybody's familiar with whitelisting, right? Yep. So whitelisting is our godsend for what we're doing here. Control systems are designed to do one thing. They don't need to be all things to everyone, like, say, an IT or a corporate network. When we set up these control systems, we expect them to do one thing and one thing only. So once we defined what that one thing is and that only thing is, we can lock down what done looks like, and we won't allow anything else to run on our systems except those particular things. So whitelisting is certainly a benefit to us that we have over, say, other industries. And then finally, there's syslogs. So syslogs allow us to, throw alarms, if you will. Dave logged in at this time, and Dave changed settings, so we can gather all that up. So it's a great forensics tool for us to monitor and see if anything happened. And finally, up at the EMS level, or the SCADA level, we have logging at a wide level. We have alarm reporting, where these alarms could be coming in from multiple different sources. Measurement consistency, and this is why I like our another benefit we have is that our systems are over measured. At the SCADA level, we can take in all these various measurements, whether it's synchrophasers, metering, and those other things, and do a consistency check to make sure that, yeah, the system really does agree that voltages are what voltages are, current flows are what current flows are. We have communication monitoring. It's all centralized at this point, and centralized can be good and it can also be bad from a reliability standpoint. If you got all your eggs in one basket and it's centralized and that system goes down, you have a problem. But we have learned to design systems so that they can fail gracefully, so it's generally not a big problem. And then we can do trending too, to say, you know what, I know during the afternoons my voltages, my power flow should look like this, in the evening they should look like this. So we can use these capabilities as a function of time to see, is my power system behaving as I expected would under normal conditions? And if it's not, we can take a look at it. Oh yeah, maybe there was some kind of aberration and that's okay, or there's something else going on. So with all these tools, we can build on our security profile. So a lot of these things maybe we haven't considered, or maybe we should revisit. So connecting alarms to other systems and equipment in our systems. So connecting that contact output alarm to an independent device like an RTU that has a separate communication channel is an easy way to add some visibility into the power system. When there are events, we can correlate all available timestamped reports. Synchrophasers is really allowing us to do that, to really correlate to some very precise measurements, all the data is in our power system. So it's not like, pre-synchrophasers where we had SCADA systems and they come through asynchronous scans and the measurements are a little bit fuzzy. With the advent of synchrophasers, we really do have a very crisp picture. All of that data can be brought in and we can use it to do a consistency check. Now you can say, well, what about the vulnerability to GPS? That's been in the news a little bit lately. I'm going to talk about that in a few minutes too, so we'll address that too. We can create those custom alarms like I talked on the previous slide. And here's a fun one, creating secondary communication paths to notify when a probe or attack is underway. And this is an interesting one. So we have a lot of equipment out there that is maybe we put it in for a particular primary purpose. It's serving that purpose great. However, if we think about it just a little bit more, maybe there's a secondary way we can use this existing equipment to provide some redundancy for the task we're trying to accomplish. Here I got an example that we've implemented in a couple of places. It's a secondary communication channel. So at the top I have my SCADA master. He's talking to 3 different substations. Each one of those has a PLC in it, and the relays are then connected to the PLCs and also monitoring currents and voltages and operating the circuit breaker. One of the things we like to do is pilot protection. We'll use radios between the between the substations. Here we can see on the left-hand side, I got a radio talking to the other relay in the middle substation, and they'll be sending trip or block information. 1, maybe 2 bits of information back and forth, and the channel in the radio is usually pretty large. So we have a lot of unused capability inside that radio link. And so in a normal course of business, the PLCs are grabbing information out of the relays and reporting those back up to the SCADA master. If, however, I lose a link, either a denial of service or so let's say the communication link just absolutely fails, I no longer have visibility at the SCADA master down into that particular substation. So one of the options we have to do is create a secondary channel. And what we can do is, instead of sending the data up through the PLC, I can take advantage of the bandwidth available in those radios and transmit the SCADA data over to the adjacent substation and then map that up through the PLC. So in this case, I'd go from the radio that's on the left-hand side in the middle substation over to the left-hand side of the radio, up through the PLC and up to the SCADA master. Now I may not be able to send all of the SCADA information I was traditionally through the PLC, but I can certainly send things like voltages and currents or circuit breaker status to give me some insight into that particular power station. Which is really, it's a nice reuse of resources without adding a lot of complexity or new equipment to an existing infrastructure. So analyze redundant and related measurements. State estimators purge bad data. So we get in our watts and our VARs and our voltages and we try to converge. But every once in a while, if the topology doesn't match the analog measurements we have, the system may not converge. And that could be a clue, right, if the state estimator isn't on converging. Synchrophasers and wide area measurements can be used to detect measurement disagreements. And I think that's one of the best benefits of synchrophasers. Not only can we use it from an optimization or a power flow standpoint, we can also use it as a consistency check. I think Pete and I were talking last night about, hey, maybe you combine those two bullets together. If your state estimator isn't converging, what is your synchrophaser system doing, and converse to that. So that's another set of system checks we have. And I hadn't thought about that. Well, I probably should have, because I had the 2 bullets together. But Pete and I had a great conversation about that. So there's a lot of this useful information if we just put our heads together about how we can see what's the state of our power system, is it being spoofed or not, by using these things, these tools we already have in hand. And then using simple meter checks like I talked about before. Our relays have measurements in the fundamental and in RMS. We can use those as consistency checks to make sure that the data we are receiving back up at the operation center, which we're using to control the power system, is valid. Our best cybersecurity practices. So use cryptographic protection, serial, and Ethernet connections. There was a time where we thought we could just take IT best practices and apply those to these operational control networks. And what we found is, certainly let's take a serial link, is when the designers for these serial links, these SCADA serial links passing, say, DMP, they used almost the entire bandwidth. So trying to stick in say a block cipher into these full serial links just wouldn't work. We'd start dropping data. We didn't have enough processing time to send all the overhead of a bunch of cryptographic protocols. But we're smart engineers. We figured out how to optimize these real-time situations. So we have come up with solutions that are cryptographically strong and meet the needs of real-time communication. So there are available solutions out there right now to do that. Create clear network segments connected by firewalls. I think that goes without saying. These days, people are really getting the need for segmenting networks, making sure that they're not flat, that there's and appropriate access controls put in place. Isolate control networks with DMZs. Use static routes. Again, my kids probably say I'm a control freak. I don't think I am, but there are things like static routes, and in control systems, we want to control everything, right? Leave nothing up to chance. So the more we control, I don't want to leave this up to a switch to figure out what's the best path. And we've been doing some research with software-defined networks, and I think that's very promising. Again, it gets back to this control perspective. Disabled unused services. So if we have on the front of IEDs serial ports or USB ports, if you're not needed, we should disable those things. There's no reason to leave a service open if it's not going to be used. Implement a patch management system. And this one actually has been a little bit different for the power engineers than I think for the IT guys. Now we have devices that have sophisticated operating systems. Every once in a while, we are going to have to upgrade or patch the particular system. So having a well-defined patch management system where you're going to get notification from your vendor, you have your 30 days to evaluate it, how you're going to roll it out based on your evaluation is very, very important. So it's not hard to do, but it's something we need to think about given these new tools that we're using. And then finally, there's this baseline IEDs and system settings. And this one is probably the most important bullet on this particular slide. Again, we set up our control networks to do one thing. That is our baseline. We shouldn't ever, those settings should not change unless somebody's come in, done an engineering evaluation, and then reset the baseline. And there's a lot of things we can do with the equipment we have in there right now. We can at a periodic rate, go out and pull our IEDs to say, hey, send me your settings, and we can compare that against our baseline version. If there was ever a mismatch between what I read out of the device and what my baseline settings were, we can throw a flag to analyze. Did somebody just make a mistake and made a setting and didn't record it as they should, or did somebody or something get in there and manipulate what the settings were? Examine logs. All these devices, whether it's the IEDs, the network switches, all these things generate tons and tons of information. Obviously, the key is how do you evaluate all this information coming at you. So elevate critical logs, making some kind of differentiation between did somebody just log in or were their settings changed. Program IEDs to alarm when settings are changed, and that's a key one. That certainly shows you when there's unauthorized access to a device. And then archive these logs for post-investigation. And that's pretty easy to do these days, and memory is pretty cheap. So we can go through, if there's a power system event, we grab the event reports, the SCRs, any of those things, we log them, and then we can put together a wide area analysis of what happened on the power system. Incident response plans. This is also becoming more and more important. So prepare the organization, let folks know that if we have a problem, this is what we expect to do. Create a team that is stood up and understands what their roles and responsibilities are. Ensure that our IEDs and other things are set up to help us resolve these problems so that event reports are turned on and we're recording the information getting stored when they are generated. And then develop and practice the remediation plan. Our IT department at SEL reports to me, and one time I asked our guys, hey, we're engineers. Our lives, really are based on these computers. If we had a computer problem, that we got infected or whatever, how long would it take us to be up and running? And there's 800 of us engineers, so we all need our computers. If I was to walk into work today and our IT guys came up and said, nah, we're down. Right? What do I do with 800 engineers, right? I guess they get to go home for Christmas early or something like that, but it'd be very expensive to the company. So I asked them, it's like, how long would it take to get us back up and running? And they said, 4 hours. And I said, prove it, right? And so then they had to come in on a Saturday and actually prove that if we had to do a ground up start, that's how long it would. So having a plan is one thing, making sure you can execute the plan is the next more important step. Okay, create a security awareness program. Training is everything. Provide regular training. We have at our place, our IT guys put these together. So every day you get into an elevator or something like that, there's a new poster. When we turn on our computers, there's a little log-on sign. It kind of gives you a security reminder of what you should and should not be doing. Notify employees immediately of threats. And that's the one help we can certainly have from the government too, is they have a lot of information on what's going on, and being able to share that with the right people at the right time is very important. So being able to share that information down from the government level, down at a utility level, down at say our level as a supplier is really, really important, so that we know what's going on, and based on that we can help prevent problems. And then finally, conduct regular security audits on your systems. One of the other things, and I added this slide from our previous presentation, is what we talked about, the website where you would log on to it. You thought you were downloading firmware from, say, one vendor, and it was really not their firmware. Things that we've done to help how would you know is, if you download some firmware from us and you want to stick it in this case, a 411L, how do you know it really came from SEL before you stick it into the device? How do you know it wasn't intercepted and somebody manipulated? So what we do is we publish an MD5 hash and a SHA-1 hash on each one of our firmware. So if you receive the firmware from us, you can go run this hash on it, and they better match those particular numbers, or you know it didn't come from SEL. Similarly, what you can do is read the firmware out of relays and compare it to these things. So these are additional checks you can do to ensure that what is running, what is baselined in your system really is what it should be. And then another thing that has come up, and this has been in the news quite recently, is GPS spoofing and the ability to manipulate time. And more specifically, how it relates to us is, what are the implications then of GPS spoofing to synchrophasers? Because that's, it's basically a precise analog or digital measurement associated with a particular time stamp, a very accurate one. So lots of news about it. What I would suggest, again though, communications, time is a convenience. We really like to have precise times, but I could still do line current differential protection, I could still do power system protection, a whole host of other activities without it. Now, again, like communications, precise time makes our lives very, very a lot easier than without it. So we'd like to do everything we can to ensure that it is reliable, precise, and not compromised. So develop distribution time systems like our network systems. And we really, at SEL, we took a new approach to it, right? We're really good now at designing networks and layers and redundancy and stuff like that. And we started looking at how really our time systems set up in a substation. And if you think about it, really, generally what happens is there's a GPS clock, and then there's a handful of RG8 or whatever the cable is. We're going to go from the output, say, of the iRig connector on the clock, the satellite clock, out to the various IEDs in the substation, or maybe it's PTP now. But essentially that was it. And is that really a robust time distribution system for critical infrastructure control? And I think there are better ways to go forward doing this, and we'll talk about those in a second. But it gets back to creating a fault-tolerant system, and for really critical systems where we're doing synchrophasers, say like on 500 kV systems or something like that, don't believe just one time source. So we thought about it and said, here's our layered approach to it. The first one is, and this kind of seems obvious, but camouflage your antennas, right? If you're going to be spoofed by a radio transmitter or something like that, don't make it obvious, right? Hide it in a place that is not obvious, so they don't have direct access to your antenna input. The next one is well, there happens to be two satellite constellations, full satellite constellations, that are other from India and China starting to stand up a GNS system. But right now, GLONASS and GPS are up there. The modern satellite receivers right now receive both of those constellations. So we can compare GPS and GLONASS. If they disagree, maybe the GPS is being spoofed, maybe GLONASS is spoofed, but we can alarm on that. Another way to do it is I can use terrestrial time distribution, certainly over, say, like SONET systems or TDM systems. I can distribute precise time over a wide geographical area, and I can compare that against a local source. Say in this case, I have the 2488 and the Icon system plugged into a 3400, and the whole part of this 3400 is what we call an IRIG-B verification system. And what it'll do is it'll compare the two time streams. If they disagree, it can throw an alarm. And then finally, all the way down at the IEDs do a great job of checking certainly the frame structure and the robustness of the IRIG signal coming into it. If they find a problem with the IRIG signal, they can throw a flag and disregard all protection or other elements that rely on absolute time. So one of the ideas that we came up with back to this IRIG verification is I can have that time distribution on that ring, so that's that wide area distribution. I can also have that GNS clock, and what will happen is I'll bring in both those signals, and let's assume that the GNS clock is now being spoofed. What it is telling me that's coming out of it, the receiver still thinks it's a good time, but it is slightly off now. So let's say it's moved 200 microseconds or 300 microseconds. Keep in mind, we're using time, or precise time. 1 electrical degree, right, at 60 hertz is 46 microseconds. So if I start to pull this off, I could start making control decisions based on, these precise times, which, I could have phase angle problems based on absolute times that are being spoofed. So this device will come in, it'll measure the rising edge of start of second, and if the time qualities for both signals say, hey, I'm good, but the device says, why would your one edge be 400 microseconds off from the other? That's obviously you either have an equipment problem or one of your antennas is being spoofed. At that point, what the device can do then is two things. One, it can go into, I'm not going to believe anybody, and go into a holdover mode and just send out its own relative time to the devices connected to it. Or two, it can force bad quality bits at that point and rely on the end devices to say, hey, the time you're sending me no longer is good. I'm going to disregard all of it. I'll keep using it for non-critical applications, but I'm not going to use it in any other critical applications. The other part about it is, let's assume I have these two constellations and I am being spoofed. I can use the almanac information I get from a terrestrial one that says to me, hey, where should the satellites be, and compare those both to, say, the GPS and the GLONASS as another absolute check to see if the time, there is agreement between where I think satellites should be and what I'm actually measuring from the satellites themselves. So what I'd do, well, these kind of seem obvious, but I'd never connect SCADA to the internet, and you should audit this. Most people would say, we never connect our networks up to the internet, but every once in a while, maybe a contractor comes in or something else that accidentally, these things do happen. So we need to be vigilant to that and make sure we monitor that. Operate private and secure control system networks. Consider TDM, and TDM, if you don't know, is time division multiplex, so it's kind of the opposite of IP. But these systems are prevalent, and from a control system standpoint, TDM is a great solution. Apply defense in depth, layers of security. We talked about those both from the cyber standpoint and also the time distribution standpoint. Maintain private security plans. There's a lot of emphasis to, hey, show me your plans, let's publicize this stuff. And there's really no benefit to a utility or any other end users, right? These things should be treated as, quote unquote, top secret material where it's a need to know situation on how we control what our security plans are. Again, back kind of on that need to know thing is compartmentalize the knowledge of the system. If you have a need to know on how systems are configured or how they're used or deployed, then you should, as part of your daily job, you should know what's going on. But if there's no reason, the janitor doesn't need to know what the network configuration is. So keeping it at, practicing good security. And then finally, what has a lot to do with you guys is the learn and the educate, right? The world we're working in now is dramatically transforming with new technologies, new capabilities, whether it's synchrophasers or new network topologies and things like that. So this is a never-ending journey, if you will, in terms of the learning and the educating. And it's both for you guys, great for doing the research and coming up with great new solutions and things like that. But I was talking with Tim, and I didn't know you guys were doing this, but the training aspect of it too, right? This is a very complicated, or can be complicated, work environment we're in. So the ability to go out and teach others about, hey, these are the new ways to protect your systems is vitally important to our industry. So thank you guys for all the great work you're doing out here. And so, in conclusion, every cyber crime, certainly in our industry, leaves some kind of fingerprints, right? Whether it's event reports, SERs, syslogs, all these things. So, if somebody does get into our systems, there are a lot of ways fingerprints get left behind. Most equipment has features that can be used to detect signs of cyber attacks. We just need to scratch our heads and see how we can use those particular features. Combining features to give us this consistency checks, as we talked about. And if you'd like to read more about the paper that kind of generated this presentation, it's How Would You Know? It's at sel.com. Feel free to download it. And with that, are there any questions?
Hi, I'm Carl Gunter, a professor in the computer science department. It's a really intriguing lecture, very interesting how much has been done on this and how diverse the topics are. One thing that was interesting to me, though, was that usually I find dull the slide that says apply best practices. But in your case, the best practices slide was a little interesting to me because it had a few items on it that I wondered whether they were at least my conventional wisdom about best practices. For example, using a fixed route means that if something goes down, you lose the connectivity. SDN means a central controller, which means if that goes down, you lose the network. So I was wondering why these are classified as best practices, what you're thinking on this.
So from an SDN standpoint, really the way I like to think about it is I'm going to define my primary route from, say, A to B, and maybe it goes A, C, B, or something like that. If I lose that particular route, what I want to have is a pre-configured fallback route for my systems, right? And when I say, so what I'm looking at from the SDN standpoint is that I have configured primary routes and then my fallback route A and my fallback route B. So from the control system standpoint, I've thought about all my various failure modes, and if they occur, what am I going to do? Does that help?
Yeah, well, yes. It's just that it runs in the opposite direction to decades of experience in resilient networking for the internet, where we have brilliant algorithms that do that automatically through all levels of fallback and in a distributed, manner. So having like a list of fixed routes, what happens when you get to the last one of your set of fixed routes and there's still connectivity, but you can't find it because you just had a list of static routes?
And we debate this all the time back at SEL, and it gets back to I'm a control freak, right? So I always want to know exactly which route my devices are taking. And I understand there's been a lot of research and a lot of optimization for which is the automatically determining which are the best routes. But from a control system standpoint, it's always nice to be able to enumerate all the various ways I want the power system to operate. And finally, like we have talked about, let's assume for whatever reason, we have an N-3 contingency or something like that, which everybody can say that's a really bad day. The end devices, usually the ones I'm talking about from the control and operation standpoint, even if they did lose their communications, generally have some level of protection to be able to control the power system. So even in your worst day, you're still, certainly from the control system side, you'll be okay.
So my summary thought on that was, it'd be interesting, what it made me think was it'd be interesting if we had some way to do tests or experiments to compare those approaches. Like, whether the internet-style protocols were under some measure better or not as good as a list of static routes.
Well, I think that can be a
discussion for later.
A project for Dennis. No, because I'll be the selfish commercial guy on this side. Is I really do like SDN, right? But comparing it and contrasting against other alternatives is certainly part of my job to say, hey, this really is the best control system solution, and here's the data that shows why it is, right? So having these races or tests or what have you is I think, one, a great research topic, but two, it has to be done just to prove out and vet the system before we go broadly deploy these things anyway.
Yeah, thank you.
Yep.
Tim Yardley, University of Illinois. So I guess two questions. One is a point and the other is a question. point is, I like that you had learn and educate effectively in there as a method, and I believe that workforce development is an area that we definitely need to work on broadly, not just in this sector. And we're doing a part of that, but there's lots of other people that need to work on that too. So that's the point. Now the question. One, I think it's 2 slides back, you had a statement that said, never connect SCADA to the internet. So to be a bit contrarian for that, is, sure that's perhaps, avoidance, right? It's don't connect it to the internet, and it probably doesn't have a path. But that also harkens back to we're air-gapped, we're fine, and then it causes lax protections and other things. So the question, how do you feel about the notion that these systems, regardless of how they're connected, what they're connected to, et cetera, need to be resilient, need to be defended, need to be protected so that you can have your control system connected to the internet and it doesn't matter?
So my simple answer is I agree with you, right? We don't want that to happen, but at the end of the day, bad things are going to happen. So we have to take that into consideration. So I put that up as the first bullet, but I agree with you 100%. There could be times where it happens unintentionally, but from a design standpoint, ensuring that if it does or if it were, it could still be resilient is certainly paramount to ensuring you have a reliable and a robust control system.
Yeah, my name is Prosper Panompavi. I am a power research engineer and RTD as a subject matter at the University of Illinois. It looks like to me that there is a few schools within the nation which are teaching protection in the university. Mm-hmm. I always believe in my dream that at the University of Illinois, it should be in the program course teaching protection. But bringing a change to a program to the university sometimes is tough. And this can happen if there is some interest shown from the industry. So my question was, is there any way that we can work with Schweitzer in a way to bring a protection class at the University of Illinois that will improve really the understanding of cybersecurity? Thank you.
We have worked a lot with the various universities. Certainly, maybe University of Idaho and WSU get a little unfair share of our attention, but that's only because they're in our backyard. But we provide guest lectures and things like that, so we can work with Pete and everybody else to come out here and lecture. Love coming out here. It's easy to, well, it's not easy to get here, but it's fun to come out here and work with you guys. So if maybe Pete can work with us, and maybe there's something we can do.
Hi, this is Grace Gao, also from University of Illinois. First of all, thank you so much for the wonderful seminar. Since my expertise is on GPS, so I'll ask a couple questions related to the second half of your talk. So the first question, you mentioned that you can do the comparing GPS with the Russian GLONASS, right?
Yes.
Comparing the two constellations. What if there's a weakening attack? In other words, what if an attacker will record the legitimate GPS and GLONASS signal somewhere else and just at a different time and just will rebroadcast to the substations?
Right. And so this gets back to my education and training, right? This will always be one more thing. So our first solution was, okay, let's compare GLONASS and GPS. But to your point, what if they did do that and did it? So that's where you went into that next tier where I had another input, right, that terrestrial time source that was different from, or geographically, spatially different from the local GPS receiver. So that's how we'd use to compare a difference from it. But, we can go through this. There's another Iridium satellite to put out a time source. We could use that as a third one, right? But again, there could be some weakening and things like that.
Yes, thanks.
So it's a tough problem, though.
Yeah, that's why I'm also working on this. Yeah, and then related to that, when you incorporate this terrestrial network of local clocks, is there a problem if there's a delay in terms of communication?
One thing what we do is you can compensate for the delay. We know how far the different item or elements can be, so we can compensate that. In fact, we do that in our GPS receivers right now. We know that it's probably the speed or the signal traveling through the cable is probably 0.6 the speed of light. So we'll compensate for the delay through the cables and things like that. So we can compensate for those times if we know what the distances are.
Okay, thanks.
You're welcome.
Hey, my name is Yasser. I'm a student here. I noticed on one of your slides you had a point that every attack would leave fingerprints.
Yeah.
And on another one of the slides that there's points where physical access was available to your networks and your systems. So I was wondering, have you ever thoroughly vetted that? Have you played the role of an adversary and tried to mount an attack where no fingerprints would be left?
That's hard, right? Because it's not hard to answer the question. Yeah, we try to go through all the various scenarios, right? And if we can go through the scenario logically in our mind, then obviously there was a fingerprint that got left. The ones that would be challenges, somebody really did sneak in, we didn't know about it, so we didn't at that point find the fingerprint. So it's kind of a tough argument, I think, if I'm understanding your question correctly, is could there be an attack where there isn't a fingerprint?
Yeah. And I mean, maybe hiring outside people to come try and have a go at your systems, this kind of thing.
Yeah, and we have participated in a lot. If we're talking about, like, say, penetration testing or those other things, yeah, we have a group that internally does that, and we've worked with others that have looked at our equipment.
So you're confident every attack leaves a fingerprint?
No. Well, there's two things. The systems, there's I would imagine there is never going to be something that is 100% cyber-proof or what have you kind of thing. And that's why we have to build up layers of protection on this in case there is a shortcoming in one product that we have redundant, or we have layers of protection to kind of protect us from that particular shortcoming. So this is, we get back to the teaching and educating. This is going to be a continual game where we need to reevaluate, analyze our particular products, our solutions, our systems, right? And then step up our game, every single day. So this is going to be an ongoing battle for forever. There is no, all right, the answer is 4, we're done, let's go home and eat dinner.
Thanks.
So, Dave, I wanted to ask a question, but I've been told we're out of time. So maybe I can ask you afterwards. So thank you very much. It was an incredible talk, and thank you for your interaction and support with us on TCIPG.
Well, you're welcome. Thank you for having me.